So we can find here in the Ethereum specification all the things about the Ethereum 2.0, and we have this folder that is interesting one, and it's called papers. We have the papers, that is the first research about the Casper, and we have different drafts and different papers that are published in different hubs of research. Very nice hubs of research, and it's an incredible research about the protocol. And we have here the first implementation. That's a very nice paper about the things that Ethereum 2.0 have. So let's see, this is still lined right now, and we can download to have a better to see this paper about the first implementation, and we can saw in this beacon chain implementation all the papers that we have. So far we have here the first paper about Casper. And it's interesting paper. The thing here is this paper starts to thinking in how it can be consensus state topologic. What does mean? How this blockchain could start to make another chain and don't make how do you say a failure network. I mean, if you have a one state and you want to make a topologic state, that the one state starts to make another state, this can be adaptation of this protocol. And we can see that the first adaptation was in the paper of Sam Polonsky, and it's called the Grady Heavis Observed subtree that is called Ghost. And this Ghost is start to thinking in a four-choice rule. That is the first implementation about this protocol. And this protocol start to make an interesting comparison for the traditional consensus, and start to think in how this Ethereum 1.0 start to make a scalability, and this scalability needs to be a huge amount of transactions per second, a huge security, and a huge manage things on the network. So far we have all the basics here, and we can see all the math and lemmas and theorems that start make definitions about this protocol executions. And we have start how this binary estimate start to make sense in how this protocol states make the protocol execution, and then start with the Python script wave for make the live world implementations. Protocol executions. So we can see here the first experimental observation about this protocol and implementation of the Grady Heavis subtree that is called Ghost, that works in a some way like a four-choice rule. And this for choice rule, it's a way for understand the protocol in so many ways. Then we have another interesting approach about the decentralized thing. And we have here how this protocol start to make the protocol implementation and started thinking in the beacon chain and the beacon state. Also, in Google, you can find the client that is called in Ethereum Trinity. You can find over there that is the Trinity client of the Ethereum protocol. You can find here, and it's writing in Python. So let's see this data because I like the underhood stuff. So let's move and start to see the code and the maths and lemmas and theorems. But let's see. And let's see this open source. So we have here the beacon chain in this folder. Let's see this folder and we can find the beacon chain. So we can here this beacon and we can find here experimental code, but that have a production sense because this client is going to live in the next month, and we can find here how these scripts start to make sense and the evolution of these scripts. So we have here the first scripts that talk about the protocol specification about the beacon chain and how this block will work, how this block will be verified, the random thing about the security that the protocol needs, the validation thing, and started thinking in interesting meanings like the crosslinks. Then in another videos we saw that the crosslink is the number of attestation that the beacon chain state needs to validate the beacon chain and the shard chains itself. And we can find the first field about this kind of protocol. So let's see some code of this. Let's open the folder to see what it's about. So let's see the open source code that we download and go to the downloads. And we can find here so it's here but it's not working. So let's download again to see what is going. because the compression stuff is not working. Okay, let's download again. And so the open source code, download the zip, and so what is not working because it's not working here. We have here this tensor, but it's not compressed out. So let's start again. Okay, let's see here code. Okay, it's not working so good. So let's see the beacon chain, and we have the different implementation. The first implementation that we saw in the protocol is the for choice, that it's based in the paper of Sokolowski, that it's calling the ghost, that we can find here, that Sokolowski make the meaning of the greedy Hibis observed sub-tree. That the first instance about this is the height of the chain. So the height of the chain will be the leader or the thing that needs the protocol to make this transaction of one consensus state for the other consensus state in some mean. So we have here the implementation, and we can find that the first script start to thinking in this cross link and how this beacon chain start to connect with the other chains that is calling the shard chains, and these shard chains have the shard blocks that have different meaning. So the kind of connection of this thing will be a cross link, that it's the number of attestation that needs to have to connect and validate like the beacon chain needs. And we have another kind of terminology of glossary that it's calling the slashing conditions. That is an interesting way to see how can be slashed, that in another meaning can be not pass the protocol for reach the consensus because could be negative. And also we have the beacon randomness, that it's how this beacon chain starts to make a random thing or random inputs to have an extra layer of security in the meaning of crypto primitives, because you have different chains that you can start to thinking different kind of vectors to attack this consensus and make a Byzantine fouler, or maybe make hijack, or maybe make different things that the consensus, the Byzantine consensus, don't need to make a properly think for understand the protocol. So we can find here this incredible Python script that how this beacon chain start to make the process attestation. For example, we have here this line of code the process attestation. That is interesting way to see. So let's replicate this code to understand the things. And it's not working. So let's make a new file. We can find and name like beacon pie. Okay, we have here So we need another name like icon. Okay, it's not working very good. So let's new file and see the beacon state that Python. It's not working. Maybe it's a use that we have here for a long time. Okay, so let's start to make this Python script, and we have the dev process attestations, and we have the validator set, we also have the attestation indices and other instant the attestation. That is probably the attestation balance. It's max. Okay. Interesting way. It's max. The message itself is aggregate sync. Okay. We have this first script. Then we have a way to see this one. And then we have the balance of delta. Balance of delta. It could be anything. And then we can see how this assert of the length of the attestation start to make how this attestation print the values and verify the aggregate sync. So it's an interesting way to see. But let's see in the Trinity client how this evolution in the process attestation. We can find here so we can find anything. Okay, let's see in the chains, and we have the base beacon chain, how this start to make the state machine classes. So let's move in another. We have here the helpers of the attestation. That it's an interesting part to see how this attestation works. And we can hear how this attestation start to have an index of this attestation, and we can find the first script that this is only process attestation, and how this start to make a better performance in the protocol statement. So let's see how this is work. Let's see this function star to see in the protocol implementation. So we can find here this process attestation like in import, because it's more interesting, and we can find here the slashing conditions. So process attestation, let's see this import to understand how this is working. in production code. So let's see, process attestation, and we have here the same data. Okay, let's see from where is from all the beacon state, import validate state. Also, you can hear that this data make a lot of things about, and the interesting thing is also the signet voluntary exit. So so it's interesting how this script start to make an evolution in technical way to see, because we can see here how this attestation is calling bitmax. We can see how this bitmax evolution in the Python code to understand better attestation. We can see that bitmax is not working here because maybe the protocol specification changed a lot. So okay, we have here the protocol specification, and I start with the attestation data. This have the attestation data is a class, needs to be have this data, and it's all about how this FFG vote, that is variant of the Casper implementation, can see a thing in the checkpoint, because we need to connect this beacon stake with another chain that it's calling the shard chain, and it's an interesting way to see how this protocol start to make an evolution. And we also have the index attestation. That index attestation is about how this validator have the meaning of the protocol specification itself. Have the pending attestation, so we can find the attestation data, start make a better protocol specification about this, because we can find here in the first process attestation that we have the bit masks, because it's a script, and we can find that we need to verify it of this message. We can have the poops, so these poops start to make a better protocol specification and start to think in this class attestation and the indexed attestation. Depending attestation, because you have a queue, you have a bunch of this attestation that need to start to thinking in how this attestation starts. So it's an interesting way to understand this attestation. So this thing is not working. Layer 1 maybe is failing. So let's leave this program and start again. So we can find here this index attestation. So on the protocol specification we can see that this attestation have different things. So let's see this thing, and we have here the attestation that is called dev prof attestation, and we can see how it is changed across for the first simulation in the script. And we have here that this process attestation have this data for the attestation and how this data index get the commit account and the slot. I start to thinking how this make the commit, forget the beacon commits. Started thinking independent attestation and the statements of the discrete matter that we can find to make the thing that we have. So we can find here how this code make a better performance the technical way. Because we can find here the verified message, agree pools, and start to make this evolution in the assert it's validate dex set attestation, and we have the state and get index set. So we can find here comparison of this and how it start to make more sense. So we have this kind of code. We can see how this verified is validated in a better way in indexed. So it's a technical way to see how this attestation start to make more sense for the protocol. But all the math is the same. So it's an interesting way to make a technical identification of the code. Okay, so okay. So let's see more about this attestation. So we can find here the process of the attestation. Then we can find in the way that it's import from the it beacon, that are the tools that have different condition. Let's start to see the beacon state in the process of this attestation and how can be good for the specification of the protocol. So you can start to understand with me the things that the protocol have, because we can find the obvious thing about this, how this script start to make a evolution in different ways. So you want to make your own BFT protocol and you want to make a relay word, it's a good way to start to make this and think how this attestation works, because the attestation we can see in another paper that have different meaning but have the same goal, that is reach the consensus in a different way to get it. So it's interesting. So this kind of data in the protocol. In the way of the leader-based Byzantine fault tolerance, because we have, for example, the leaderless Byzantine fault tolerance protocol, that is another way to see that are based in inequalities, in samplings, subsamplings, and binary things. Another way to see this kind of protocol is the succinct Byzantine fault tolerance protocol. That's another way to see this protocol. But right now we are thinking in this process attestation and figuring out how these initial papers start to make evolution in the protocol, and start with the first draft of this protocol and the evolution of this paper. That the obvious thing that is make a better BFT protocol, and the thing here is that if you have a better BFT protocol, you have better performance in the network. And we start to thinking in the scalability issue, that it's the trilemmas thing, and this trilemmas thing it's the security the most important, because you can have a good scalability, but you can have a very good security in the protocol. So this is interesting to see, and we can find here the Casper basics that we saw in another video to understand the things about the protocol. We have the correct back construction of the consensus, that it's another part of the phase. So we can start to thinking here that maybe could think in the phase 0 of the protocol specification. So let's move to see more about these scripts, so we can see the first full post implementation of the Casper and the progressive Merkle trees, that it's about the Casper basics, how this Merkle root will work in connect all the branches. So we can see short script how this add value to the Merkle tree, and Merkle trees are always interesting. So we have this replicate for understand the weight. So we have the depth value, we have a branch, the index, another value, and how this start the condition that you want. Well, you have an index plus thing, and you have this thing, the condition of the protocol, because remember that you have different chains that is calling the shard chain, that is making another kind of data that have this protocol. You can find here the evaluation of this. Remember that in the Python world, all it's an object, so the value needs to be a hash in the branch. The condition of protocol is so you have the branch plus the value and the things that the branch needs. This state is calling the J state, so this branch E that you have in another way is connect with the value. And we have these values start to think how make. So it's an interesting way to see how this Merkle tree get the root from the branch and start to make the things that the Merkle tree do it, that it's compare so fast the data that you have. And we can find here different problems that are calling the data availability, because you cannot think how the finality of the consensus make the thing that the Merkle tree have the data that is, because you only have how this it's only get the roots, but you cannot figure out how this data have in this branch. So I think that Merkle tree have the data availability problem, and this data availability problem It's a big deal right now for this kind of attestation approach, meaning a proof of stake that needs to get data for one main it chain, that in this case is the proof of work chain. So it's an interesting way to make the data. So let's see here how in the technical meaning this Merkle tree starts to have another sense in the protocol specification. We can find anything. We can find here how it's imported, how the Merkle proof start to make sense. So the data availability problem, it's a current issue for the Merkle tree comparison and how this Merkle thing needs the proof. Could you have a lot of chains? So let's move to see how this Merkle tree works for comparing the data in the protocol instance. Well, for example, in the validator, that's an important way that needs to work properly for the protocol specification. And also you can find here in the protocol specification how this work. Have beacon access source, that's interesting way. All the things have. So in protocol specification of the phase 0 we don't have the Merkle tree because have more sense in this how this beacon state start to connect with the shard chains, so you can figure out a lot of things how these make more sense. So if you want to make PFT protocol with attestation, you can figure out a lot of things in this protocol and this circle and this lemma that is about the 4 choice rule. That it's a very nice optimistic way to see how to reach the consensus. So okay, we have here in the phase 0 the Merkle tree implementation. Maybe in the phase 1, because it's well the beacon start to make these shard chains in the way that the protocol in the phase 0 needs. So let's move to another thing. In the protocol specification we have here how get data state in the indices, and we have here this thing, and we can find here in the first implementation how this def block we have, how this verify, how to get random thing, the validator thing, and it's to start thinking how make the connection of this thing and start a state that is different for the other way, so that have different fields, different data in this new state. How this data start to make the things that the validate state needs. So it's incredible script here. Of course, the rewards. So this new way of connect the data at the station. So we can now find here in the first Python script. It's only thing in the crystallate state. That is the new state of the chain. So we start to figuring out how it make sense in the protocol. And it's interesting if you like Python, if you like VFT protocols. So you can figure out a lot of things of Python, a lot of things about the VFT protocol implementation. So let's move to see this data. So you have here that the def get attesting indices. We have something that is calling the state, and in this state we have the data, the bits, and the state, and you return this set of attested indices because you, in some sense, you are encapsulate this data. So you encapsulate this data for having better performance in the attestation work or the attestation meaning. You need to encapsulate for having a better commit thing. So then in the Python mean you need to commit and get the thing that you need, that it's the vehicle commit. And you can find the same thing here, that it's here because it's the input of this data in the Python world. And then you need to return the set of the things that you need. So are the basic of this script, and you start to think it that this was a technical thing about the attestating meaning, because in the other way we can find here that in the first Python script you only have the process of attestating things, or the attestating meaning for the protocol specification. So it's an interesting way. So we have the first implementation, and now how this make more sense in the protocol specification. So we can find here that the process attestation get this meaning, the index meaning, and you start to encapsulate this data for make a better performance. And you also have update FFG and crosslink progress. Okay, so you can see a lot of things in this, how this protocol specification start to take more sense. So far we saw the attestation meaning for the beacon state in the phase 0, because you also have another thing in the phase 1 in the beacon state about attestation, because you start thinking how the shard chain start to growing in some sense. So it's interesting to see how these indices is a kind of helper, or a kind of make different. So you also have the index sec attestation. It's another function here that is object in Python. So let's figure it out this index attestation, that it's another protocol specification about how this beacon state make. So you have the beacon attestation, you have the same thing you have here, but maybe another plus thing. We have here how these attestating indices get attestating indices and return the indexed attestation. So let's see how figure out in here. So we can find here the aggregator, that's a part of the builder, got the index attestation that have the same meaning, and then we can find out how this get index attestation make the things that have the same input in the protocol specification, and in this way we can find the for choice how this get index attestation are the index attestation that the state needs. Then we have how this block validation starts to get the index attestation. So in this way we can figure out that this index attestation work different like the indices, because start to make a validator meaning, or maybe you can start to thinking in math way. So you have the discrete statement. So this discrete statement, you need to figure out how this attestation starts to work. So here the obvious thing is this get an indexes attestation have the state of the beacon state. So it's a way to prevent different things that maybe the Byzantine fault tolerance protocol don't need for reach the consensus in some way. So okay, let's see the block validation of this index attestation. So we can find that start the randoms and recon randomness, the slashing thing. Okay, so it's only start to think how this object makes sense for the protocol specification, and it's a hard way to see how this work in the protocol. But then the big difference here that you have the attestation itself, because it's the index way for the attestation. So it's a way, in a technical way, how this index attestation works better for the validator side. Yes, because you have this, the validate index attestation, and it's an interesting way to see how this state start. So the object make a better performance in so many ways. So it's interesting. So let's move to another attestation thing. It's a protocol specification. Attestation and slashing, it's a beacon operation. It's different for the attestation thing because it's this the other thing that. So let's see the other operation. Okay, we saw the data that the attestation have, that it's aggregation bits, that it could be equal to the bit max, but so So you have here the aggregator bigs that could be in some way equals to bit max, and we also have this kind of signature. That is the way. So you can see here the attestation bit max as it's the aggregation of the bits of this attestation. Also we can find the indexes that you can find there that make different way of this in a different function. Then you have the attestation bit max, that is also the aggregation of the bits of this attestation, that it's the data that attestation have in the protocol specification and have of or make sense in the way of the protocol works. So far we saw in summary the attestation protocol specification, and this protocol specification start thinking how this attestation make attestation slashing, but this will be in another video, because as you can see, one function or one object in this project have many ways to see how this beacon operation have different ways to see this is work, and the attestation is a very good thing about how to reach the consensus in the hating, in the meaning of the Casper basics that the paper have here. So let's see another look in this paper to see how this work under the hood. So download. So we can see here the hey that I'm saying, that is the hey function, that it's illustrating this how this checkpoint tree works in the hey function, and this is it all about how this justificate chain with the checkpoint tree. So this is the way how this tree is connecting in the checkpoint that the station needs, because you have a different chains in the protocol, and it's a way to see how this Casper basics works in under the hood. So far we saw data that have the attestation that we can find that have different things, that it's the thing that how this is processed, and you have the aggregation bits that could be a bit max for this. You also have that this attestation needs indices for enumerate the index that have these indices, and how the statement of these aggregate bits start to make the asserts that they need, and the assert that the attestation needs is verified, and this verified needs the way that could be singing, that it's calling in the BLS thing. So we saw this first attestation protocol specification, and we'll also have this attestation data, that is the container that have all this data, and we can see how this checkpoint that have the Casper basic that is calling the height function illustrate the checkpoint tree, how it start to work under the hood. And we also saw how this attestation have a queue, so you have a pending attestation that also have this bitmax or aggregation bits for make the data that need to propose the index and have the validator index. So you can see how these objects start to connect in the way of this head function about to make the other chains to validate the beacon state. So thank you for your patience about this attestation, but it's a lot of information, and could you see how these first scripts start to make sense to have the technical way to see the protocol. So if you want to make your own BFT protocol, it's a very good reference, a bibliography for understand under the hood how this implementation works in the real scenario. And see you in the next video.